Hello, and welcome to a short video on the mean value theorem for integrals. There are a couple of pieces of housekeeping that we have to attend to before we begin. The first is that you're going to get the most value out of this video if you already are familiar with the concept of the mean or the average value of a continuous function on a closed interval. And if you need an introduction to that topic before you proceed, I'll leave a link to a video that will explain that in the description. Item number two is that you probably have encountered already a theorem called mean value theorem that has to do with average rates of change and derivatives of functions and certain things being true under certain conditions. This is not that, in spite of the similarity of names. So when you see plain old mean value theorem, that's something else. Mean value theorem for integrals is our topic for today. All right. We're going to start with a familiar continuous function on an easy closed interval. So I have here up in Desmos the square root function from x equals 0 to x equals 4. And the idea, if you'll recall, behind the mean value of a function is that it is a constant function that encloses the same area on the interval as does the original function. So the idea is that this rectangle will be equal in area to the area under the square root function from x equals 0 to x equals 4. So we're going to go back to the document camera now and see if we can determine the average value of this function on this interval, and then see what else there might be that we can discover once we have that and once we have it loaded up onto our picture. To calculate the average value of the square root function on closed 0, 4, we have to first recall the formula for the average value of a continuous function f on a closed interval ab, and that is that f average is 1 over b minus a integral a to b f of x dx. And so in our case, we have 1 over 4 minus 0 integral 0 to 4 of the square root of x dx. This is 1/4 times, let's see, anti-differentiate x to the 1/2, you get 2/3 x to the 3/2. It's from 0 to 4. And if we simplify this fraction, that comes out to be 1/6. 4 to the 3/2 is 8. 0 to the 3/2 is 0. And we have 8/6 or 4/3. So we are back on Desmos, and I will simply add to the picture the graph of the constant function y equals 4/3. It should shock no one to see this graph of this constant function intersecting the graph of the square root. It sort of has to be that way because the average value of a function ought to be between the minimum value and the maximum value of that function on that interval. And if the function's continuous, the only way it can get from its minimum to its maximum, or equivalently its maximum to its minimum, is to go through all the values in between. And if the mean value is one of the values in between, then the graph of the function has no choice but to go through the graph of the constant average value. So let's go back to the document camera and figure out the x-coordinate of this point. Since we know the y-coordinate of the point of intersection of the average value graph with the graph of f, it should not be difficult to figure out the x-coordinate. We just need to set the function equal to its own average value. And so the function, of course, is a square root function, and the average value is 4/3. And so pretty simple equation to solve. X is 16/9. This is about 1.778. And this actually is a value between 0 and 4, which should not surprise us based on what we were saying a moment ago. It's not so difficult actually to make a formal proof of this theorem, and it's a good exercise to go through because it's an interesting argument and because the mean value theorem for integrals turns out to be important in the proof of the fundamental theorem, and of course that's rather a big deal. So Since f is continuous on closed AB, we know that it has both a minimum, which I'll call little m, and a maximum, which I'll call big M. And so all values of the function on the interval have to obey this inequality. We know that integrals of lesser functions on a given interval have lesser values. So I can say that the integral from a to b of little m dx is less than or equal to the integral from a to b of f of x dx, which in turn is less than or equal to the integral from a to b of big M dx. But now, this integral just represents the area of a rectangle that has a height of m and a width of b minus a. So if I were to go to the bother of working it out with the fundamental theorem, which I certainly could, I would get little m times quantity b minus a. This is still the integral from a to b of f of x dx. And in a similar fashion to the far left, this is big M times b minus a. B minus a is positive. There are no problems with my going through this compound inequality and just dividing by b minus a, which gives me little m less than or equal to 1 over b minus a integral a to b f of x dx, which in turn is less than or equal to big M. Now, if f is continuous on closed AB and the average value of the function lies between its maximum and its minimum on that interval, then the average value of the function must be a value that the function takes on. That being the case, there has got to be some c in closed AB such that f of c is equal to this average value. And if the function rises and falls, and depending on all the particular circumstances locally, it could be the case that there are multiple values of c for which this is satisfied, but the theorem guarantees that there's at least one. We'll conclude with a formal statement of the theorem. It's very similar to what we were just saying, and a picture which may be a helpful memory aid and a helpful aid to understanding. And so the formal statement, mean value theorem for integrals. If f is continuous on closed AB, there's at least one c in closed AB such that f of c equals 1 over b minus a integral a to b f of x dx. And when we're speaking informally, we often say something like f has to take on its own average value on the interval. And of course, there has to be a corresponding x coordinate. The picture, my cursor's in the way. The picture, here's our continuous f, here's our constant f average, and we just have to, it has to be the case that f average crosses the value of the graph of f on closed AB, and wherever it crosses, that point has some sort of x coordinate, and that x coordinate is on closed AB. If by this point in the conversation this all seems rather obvious to you, that's great, because it means you get it. It is possible to get intimidated by the notation, but at the end of the day, the ideas here are pretty graspable. And I hope that's been the case for you with this video. So happy mathing.